Section 9.3 is on simplifying radical expressions. We know that some numbers can look different but have the same value, such that 1.5 is the same thing as the fraction 3/2, and 4/6 is the same as the fraction 2/3. Negative 10 divided by 2 is the same as negative 5, and 35% is the same thing as 0.35. These are just a few examples of numbers that can be rewritten in different ways but have the same meaning. This is also true for square roots. For example, find the following on your calculator: the square root of 45 and 3 times the square root of 5. If you use the square root key, second and blue right there above the x squared key, you'll see that the square root of 45 and 3 times the square root of 5 are exactly the same value. So they are the same number, just one has been simplified. The same thing is true with the square root of 3/8 and the square root of 6 divided by 4. If you try the square root of 3/8, you get 0.6123, and if you try the square root of 6 divided by 4, they are the exact same value. So again, they have been simplified in different ways. So our goal with this section is to talk about what the simplified version of a square root would look like. So if my square root is simplified, there are no perfect factors inside of it, no fractions inside of it, and there are no square roots in the denominator. To help us out, we want to first write down the list of perfect squares. The perfect squares are 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, and 225. Okay. We should probably know at least the first 10, maybe the first 15 perfect squares, because these are the only numbers that we're going to be able to use to simplify our square roots. To simplify, we're going to start with the product property. The product property says that if the square root of two parts of a product, you can write them in separate square roots. So the square root of a times b is the same thing as the square root of a times the square root of b. So we're going to work on that first rule, that no perfect square factors can be inside of a square root. So I've got 28, and I know that 28 is 4 times 7, and 4 is a perfect square. So we're going to separate this into the square root of 4 times the square root of 7, and evaluate the part that is the perfect square. We know what the square root of 4 is. It's 2. So we can write this as 2 square root of 7. 2 square root of 7 is simplified. Let's try it again with the square root of 80. I know that 80 is 8 times 10, but 8 times 10 doesn't work for us because neither 8 nor 10 is a perfect square. We only want to divide by numbers on this list, numbers that are perfect squares. So instead, let's write it as 16 times 5, since 16 is a perfect square. So this is the square root of 16 times the square root of 5. I know the square root of 16 is 4, so I simplify this to 4 square root of 5. Square root of 75. The square root of 75 is the same thing as the square root of 25 times the square root of 3. 25 is a perfect square, so this gives me 5 times the square root of 3. And 600. 600 can be written as 100 times 6, so that's the square root of 100 times the square root of 6, or 10 times the square root of 6. Again, we only want to work with perfect squares, so 60 and 10 is no good since those aren't perfect squares, but 100 is a perfect square. That's how I want to break this up. Okay, let's look at the next page. The quotient property. The quotient property says that if you have two numbers inside of a square root separated by division, you can separate them into the square root of a divided by the square root of b. So this brings us to the second property. We're not allowed to have any fractions inside of a square root. So if we do, we're going to reduce them by putting them in separate square roots. So we're going to simplify this to the square root of 5 over the square root of 36. I don't know the square root of 5, so I'm going to leave that as the square root of 5, but the square root of 36 can be simplified to 6. So that would be fully reduced. Okay, What about the square root of 10 over 64? That would be the square root of 10 over the square root of 64. I don't know the square root of 10, so we'll leave it, square root of 10. But I do know that the square root of 64 is 8. Okay, now in part C, I don't know the square root of either 15 or 27. So unlike part B, in part B I simplified by separating them into top and bottom because I did already know the square root of 64. Instead of reducing first, I wanted to leave these two numbers the way they were because this one was a perfect square. Neither of these is a perfect square, so we're going to reduce first to divide them both by 3. This will be 5/9. Now I've got a perfect square. So now we're going to separate into two separate square roots. This will be the square root of 5 over the square root of 9. So I'm going to get the square root of 5 over 3. Okay. So when I use the rule, I can still simplify my fractions. I just need to know if I want to or not based on whether or not I have a perfect square. That third property about simplified square roots was that there are no square roots left in the denominator. If there are a square root in the denominator, I need to rationalize it by multiplying by the smallest factor that will create a perfect square in the denominator. So for example, the square root of 7 is in the denominator. I need to rationalize this by multiplying top and bottom by the square root of 7 to get a perfect square in the denominator, to get the square root of 49 or 7 in the denominator. My numerator is going to become 4 times the square root of 7, and my denominator is going to become the square root of 49, 7 times 7, which simplifies to 4 square root of 7 over 7. It's been rationalized. This is fully simplified. There's no square root in the denominator. Okay. So two things. We're not allowed to have a fraction in a square root, so we're going to separate this into square root of 2 over square root of 5, and then that square root in the denominator needs to be rationalized. So we're going to multiply top and bottom by the square root of 5 to create a 25 in the denominator. So it's going to give us square root of 10 over square root of 25, and that 25 is a perfect square. So I have square root of 10 over 5. Okay. I chose square root of 5 because 25 is the smallest perfect square that 5 will go into. Let's look at the next one. Okay. Separate this into negative square root of 7 over square root of 12. Now what's the smallest square root that 12 will go into? 12 will go into 36, which is a perfect square. So we need to multiply top and bottom by the square root of 3. I'm trying to make the bottom a perfect square. So it's going to be square root of 21 over square root of 36. I know what the square root of 36 is, so I can write this as square root of 21 over 6. Alright, try it again with 32. What's the smallest perfect square that 32 goes into? 64 is a perfect square and 32 goes into it. So let's separate this into square root of 9 over square root of 32. And then we're going to multiply top and bottom by the square root of 2. Okay, now the top, the square root of 9 is 3 times the square root of 2. And the bottom, the square root of 32 times the square root of 2 is the square root of 64. So I'm going to have a final answer of 3 square root of 2 over 8. Let's go to the next page. Okay, another property that we had before was that if you have a binomial divided by a monomial, you can simplify by distributing the division. You can write this as 15x over 3 plus 12 over 3 and reduce that to 5x plus 4. Another way to approach the same problem is to factor the numerator. You can factor the 3 out, writing this as 3 times 5x plus 4 over 3, and then divide the 3's to get the 5x plus 4. So just two different ways of thinking about that same problem. Okay. Now, we're going to use this same property that we used with variables with our square roots here to reduce when we have two terms on the top and a single term in the denominator. Okay, so 8 and 6 can both be divided by 2, and so can 10. So let's factor 2 out of the top. It's going to be 2 times 4 plus 3 square root of 7 over 10. Now we're going to reduce these to 1 times 4 is 4 plus 3 square root of 7 over 5. So this is simplified. Okay, let's try it again. divide these all by 5. So let's factor the 5 out of the top. 5 times 7 plus 3, square root of 3, over 45. And that's going to give us 9. So my final answer is going to be 7 plus 3, square root of 3, over 9. Let's look at the last two. The square root here is not yet simplified, so it's going to be our first step. We have 14 minus the square root of 12, and the square root of 12 can be written as the square root of 4 times the square root of 3 over 8. So I've got 14 minus 2 square root of 3 over 8, since the square root of 4 is 2. Now we can factor 2 out of the top. That'll give us 2 times 7 minus the square root of 3 over 8, and reducing gives us 7 minus the square root of 3 over 4. Let's try the last one here. The square root of 18 can be simplified. So we've got 6 minus, the perfect square that goes into 18 is 9. So square root of 9 times square root of 2 over 12. Or 6 times 3, square root of 2 over 12. 6 and 3 can both be divided by 3, so let's factor that out. I'll leave you with 3 times 2 minus the square root of 2 over 12. And I can reduce this to 2 minus the square root of 2 over 4. And that's it for this section.